If you just remove estrogen from a biological system, the physical changes aren't this slow, gradual wind down, right? I mean, in certain animal models, the uterus can lose something like 80% of its mass in a single month following an ovarectomy.
Yeah, 80%. It's staggering.
It really is. The organ just virtually collapses in on itself. But the real catastrophe, the mechanism that actually drives the severe clinical symptoms your patients might experience isn't just that sheer loss of weight.
No, not at all.
It's this silent microscopic starvation happening deep within the submucosa, basically as the blood vessels themselves just vanish.
Exactly. It's a profound structural failure right at the cellular level.
Yeah.
When we look at chronic estrogen deprivation, we're really observing a tissue environment that is systematically stripped of its ability to sustain basic metabolic functions.
Right.
The microvasculature doesn't just recede. The entire architectural foundation of the tissue is rapidly rewritten.
So today, we are doing a deep dive into that specific biological mystery. We're drawing on a really robust stack of scientific literature for you.
Some fascinating papers in here.
Truly, we've got prospective anatomical studies of human tissue, intricate mouse and rabbit ovarectomy models, and comprehensive reviews on the genitourinary syndrome of menopause, or GSM.
And our mission today is to uncover the molecular mechanisms driving this vascular decline.
Yeah, and we're going to confront a super surprising contradiction in the human data that frankly complicates all the animal models and reveal how losing these microscopic blood vessels fundamentally transforms the tissue structure and the local immunity. So zero overwhelming jargon, just a custom-tailored shortcut for you to understand this complex web of hormones and tissue health.
To truly dissect how this microvascular density plummets, we first have to establish the immense physiological effort required to maintain it in the first place.
But it doesn't just happen by default.
Right, exactly. Reproductive and urogenital tissues, they operate under a state of high cellular turnover. They require constant, intense metabolic support. And estrogen is the primary driver of that support. It actively, continuously promotes angiogenesis.
And it's doing that primarily through the stimulation of VEGF, right? Vascular endothelial growth factor, within the local stromal cells.
Yes, VEGF expression is heavily dependent on that continuous estrogenic signaling. It's the primary chemical mediator that tells the endothelial cells to proliferate and maintain vessel integrity.
Okay.
But the signaling extends far beyond just, local stromal cells talking to local capillaries. Estrogen actually drives the recruitment of endothelial progenitor cells systemically.
Wait, really? Systemically?
Yeah, it draws them directly from the bone marrow.
Okay, let's unpack this, because that is wild.
Yeah.
Think of estrogen as a city's master infrastructure planner, right?
I like that.
It's not just funding the paving of new local roads via VEGF. It's literally importing specialized construction crews from out of state, meaning the bone marrow, just to keep the transit system running.
That is a perfect analogy. And this constant maintenance is absolutely vital because, again, these tissues require immense metabolic support. It's an incredibly resource-intensive process.
Right.
And on top of the structural repair, estrogen acts as a potent vasoactive hormone. It continuously forces the release of local endothelial mediators to maintain high blood flow. It keeps the vessels dilated.
So it's not just building the roads, it's keeping the traffic moving fast.
Exactly. This isn't a system that is built once and left alone. It is actively, aggressively maintained day in and day out.
Which means when that systemic hormonal signal stops, the local tissue isn't just pausing its growth. It's losing the chemical mediators required to keep the existing vessels open. And it loses the progenitor cells needed to patch the inevitable daily wear and tear.
And that brings us directly to the oophorectomized rabbit and rat models in the literature.
Right, when the funding dries up.
Exactly. When we simulate chronic estrogen deprivation surgically, the physiological drop-off is immediate. I mean, we see because the withdrawal of those endothelial mediators does a lot more than just reduce blood volume. It actively compromises the structural integrity of the cells themselves.
How so?
Well, without those mediators, the intercellular junctions, the physical protein linkages holding the epithelial barrier together, they begin to weaken and fail. The tissue doesn't peacefully shrink, it starves.
So the epithelial barrier is physically breaking apart at the seams.
Exactly. The hypoxia disrupts the fundamental ability of the cells to survive. They literally cannot produce enough ATP to maintain those tight junctions. So no, the tissue cannot just peacefully downsize. The starvation sets the stage for a total structural collapse.
That paints a very grim, Very clear mechanistic picture of vascular starvation. But here's where it gets really interesting.
Yes.
The human data.
The human anatomical data throws a massive curveball that complicates all these animal models.
Yeah.
Because we just firmly established that a lack of estrogen and VEGF directly causes a severe decrease in microvascular density, right?
Right. The animal models are unambiguous about that decline. Yet when we look at Table 3 from the prospective study on the human anterior vaginal wall, contrasting premenopausal and postmenopausal subjects, the numbers tell a wildly different story.
Table 3 is honestly one of the most fascinating anomalies in the literature on this. It really highlights the danger of assuming a uniform systemic response across, highly specialized local tissues.
Let's break those numbers down for the listener. In the lamina propria, the submucosa, the nerve fiber density drops exactly as we might expect from an atrophying tissue. Proximally, it drops from 3.12 down to 2.08, and distally from 5.12 to 4.08.
Exactly as expected.
But the microvessels defy the expected pattern entirely.
They do. In the proximal third of the human anterior vaginal wall, the microvessel density remained essentially static. It moved marginally from 47.25 to 48.08 per square millimeter.
So basically unchanged. No severe drop-off like the rabbit models predicted.
Right. And it gets stronger.
Yes. In the distal third, the portion closer to the opening of the microvessels showed a statistically significant increase. They jumped from 44.25 in the premenopausal subjects to 57.56 per square millimeter postmenopausally. Wait, our entire premise is that microvascular density decreases due to a lack of VEGF. How in the world do we reconcile this specific increase in the distal human tissue with this severe decrease in the animal models?
It's a great question, and it requires us to really look at the microenvironment of the distal tissue. Biological systems are highly localized. We have to consider a couple of primary theories here, starting with a localized compensatory mechanism.
Meaning the tissue is actively overriding the systemic hormonal deficit.
Potentially, yeah. The distal third of the vaginal canal is subjected to vastly different mechanical forces than the proximal third. It experiences significantly more friction and shear stress.
Okay, that makes sense.
Right, so when this specific area is suddenly subjected to the hypoxia we discussed earlier, that combination oxygen starvation plus heavy mechanical stress, it might trigger a localized emergency response.
Oh, wow. So the cells are basically activating stress-induced pathways to force the creation of new blood vessels, independent of systemic estrogen.
Exactly. They are desperately trying to vascularize an area that is under constant physical threat.
An emergency vascular network built out of pure mechanical necessity that makes total biological sense. But what is the second theory? Because anytime we look at a 2D density metric like per square millimeter, we have to question the geometry of the tissue itself.
Right. Which brings us to the mathematical artifact theory. We know definitively that chronic estrogen deprivation causes severe thinning of the vaginal epithelium. The healthy estrogenized vagina is characterized by these deep mucosal folds called rugae,
which provide a ton of surface area and elasticity.
Yes. And postmenopausally, the sources confirm those rugae flatten out completely. The tissue becomes incredibly thin and compressed.
I see where this is going.
So consider the metric used in Table 3, microvessels per square millimeter. If the entire tissue architecture has deflated, flattened, and lost its three-dimensional depth, the microvessels that manage to survive the hypoxic event might simply be packed much closer together.
Okay, so if you compress a sponge, right, the holes in the sponge don't multiply. They just get pushed closer together in any given cross-section.
Exactly. So a two-dimensional slice under a microscope would show a higher density of vessels per square millimeter, artificially inflating the metric.
That is fascinating. So the total number of vessels in the organ has likely decreased, but the localized concentration in that tiny slice appears higher just because the surrounding tissue volume vanished.
Right. It's a perfect example of why cross-species comparisons in critical thinking are essential. The reality is likely a mix of both some localized compensatory angiogenesis due to stress and this mathematical artifact from the architectural collapse.
Well, if the tissue is collapsing and sliding to the point that it drastically alters density metrics, we have to look beyond just the blood vessels. We have to look at the scaffolding holding those vessels in place, right? The collateral damage.
The extracellular matrix, or ECM, yes. These microvessels don't exist in a vacuum. They rely entirely on the ECM for physical support. And the ECM's composition is heavily dependent on the vascular supply for nutrients. It's a tightly coupled feedback loop.
And the sources detail a truly terrifying transformation of this matrix in the CD1 mouse ovariectomy model. When the vascular supply drops, the physiological shift is massive. I mean, the urine-to-body weight ratio drops by 80%, like we mentioned.
Yes.
But in vaginal submucosa, the synthesis of hyaluronic acid, or HA, just plummets.
HA is a fundamental component here. Its primary physical property is this extraordinary ability to bind and hold water molecules. This hydration is what gives healthy submucosa its viscoelasticity.
Its ability to absorb shocks, stretch out, and bounce back.
Right, but due to the decreased expression of specific genes, Has2 and Has3, the tissue essentially abandons its hydration infrastructure, and the primary HA receptor, CD44, is markedly reduced too.
So the matrix rapidly dehydrates. It loses that crucial flexibility.
Exactly. But nature abhors a vacuum. When the hydrated HA network degrades, the tissue doesn't just stay empty. It remodels the remaining structural proteins in a highly pathological way. Collagen turnover goes haywire.
The balance of collagen types dictates the stiffness of the tissue, right?
Precisely. We see a significant decrease in the small, flexible type 3 collagen fibers, the ones that allow for stretch. And they are replaced by large, rigid type I collagen fibers.
So it's getting stiffer. But the surge in type I collagen isn't even the most dramatic change, is it?
No, it's not. The most shocking finding is that the gene expression for a protein called periostin is upregulated by almost 65 times.
Wait, 65 times? That's not just a subtle shift.
It is a massive pathological signal. Periostin is a protein that plays a crucial role in tissue remodeling, specifically by interacting directly with collagen to promote cross-linking.
And the sources draw a direct parallel here, right? They note that this specific periostin upregulation mirrors the pathology seen in pulmonary fibrosis.
Yes. If we connect this to the bigger picture, in pulmonary fibrosis, the lung tissue becomes so scarred and rigid that it literally cannot expand to take in air.
Wow.
In the genitourinary tract, this massive influx of periostin cross-links the type I collagen into an incredibly dense, rigid matrix. It severely impairs wound repair, drastically increases stiffness, and crucially, it physically traps the remaining microvasculature.
Think of it like a building's foundation, changing from a flexible, hydrated, shock-absorbing sponge, the HA and small collagen, into a rigid, stiffened concrete block.
That's exactly what's happening, and this rigid matrix is a structural reality driving the mechanical and painful symptoms of GSM.
So with the blood supply compromised and the biological highways of the ECM stiffened into literal concrete, the cells that rely on those pathways must be stopped in their tracks.
They are. It creates an impenetrable environment for your immune cells. The submucosa becomes an immune ghost town.
And the literature specifically details how chronic estrogen deprivation directly disrupts the local inflammatory profile. There's a significant reduction in basal vaginal inflammation.
Yes, specifically marked by a sharp drop in submucosal CD45+ and F480+ immune cell populations.
Okay, so what does this all mean? Because usually we're told that, inflammation is bad and we should do everything to reduce it. So shouldn't a decrease in these inflammatory cells actually be a huge win for the listener?
It's a really common misconception, but no. In this context, basal inflammation isn't a pathological fire that needs putting out. It is the tissue's standing army.
Oh, I see. It's the baseline defense mechanism.
Exactly.
Yeah.
Those markers, CD45+ and F480+ elastoma, those represent the heavy lifters of the innate immune system, like mature macrophages. But without estrogen and without adequate microvasculature to deliver these cells, the standing army is gone.
Because the delivery system is offline and the ECM concrete block physically stops them from moving around.
Right. They can't navigate through the rigid type I collagen to patrol the area. And this is happening alongside a severe thinning of the epithelium, right?
Right, and a decrease in glycogen concentrations at the surface level.
Which is critical because glycogen normally feeds the healthy protective microbiota like lactobacilli.
So the protective surface bacteria starve, the physical barrier is weakened, and the internal immune cells are locked out by a fibrotic matrix.
It lowers the baseline defense mechanisms entirely. This explains exactly why postmenopausal women become so highly susceptible to opportunistic infections and invasive uropathogens like E. coli.
Because the tissue is just physically and chemically defenseless.
Completely neutralized.
When you look at the entirety of this cascade, it's just mind-blowing. Bringing it all back to you, the listener, understanding this cascade from the initial loss of VEGF to the tissue hypoxia to the stiffening of the ECM and finally the depletion of your immune defenses, it proves that treating symptoms like dryness or atrophy isn't just about surface-level lubrication.
Not at all. It's about addressing a profound structural and vascular starvation at the cellular level.
Right, and understanding the specificity of this failure leaves us with a really provocative thought to explore on your own. We saw how dramatically the protein periostin was upregulated 65 times, acting as a major driver of fibrosis when estrogen is lost.
It's a massive lever in the pathology.
So what if the future of women's health isn't systemic hormone replacement, with all of its associated complexities? Imagine a highly targeted, localized, non-hormonal treatment that simply blocks periostin from stiffening the ECM.
Preventing the matrix from ever turning to concrete.
Exactly. Or a localized therapy that mimics VEGF just to keep the microvascular roads open, preserving the tissue's vitality and immune function without ever affecting the rest of the body. By understanding exactly how the infrastructure starves, we open the door to incredibly precise interventions. That's a deep dive for today. Keep exploring, and we'll catch you next time.